Hello, in this video we're in the weighted least squares regression setting and we're going to develop partial f-tests for the model. And as a reminder, the model that we're in is y is equal to x beta is equal to epsilon, where epsilon is multivariate normal with mean zero and variance covariance matrix sigma squared v. And then the reduced model would be represented like this: x minus x naught beta naught plus epsilon, where the column space of x is a subset of the column space of x, or x naught, and the error term is, we're going to consider it the same. So really what this is saying, that some of these beta parameters are zero. We want to test that. Are they zero, meaning we should be in this model, or are they not zero and they should be in this model? Now, equivalent set of hypotheses are these. So if we just pre-multiply everything by a positive definite matrix, it doesn't change this equation. The solutions for beta are still the same. So that's what this is. So we pre-multiply by the inverse of the square root matrix of V. And I have a video called the square root matrix if you want to learn more about that. Well, then we just generically write this as y star, x star, epsilon star. And it turns out now that epsilon star is multivariate normal with mean zero and variance covariance matrix sigma squared I, where I is the identity matrix. And then for the reduced model, we pre-multiply everything by the inverse of the square root matrix, which is this, right? And then we generically write that as y star. This is y0 star. Sometimes I'll say y naught star, but it's the same. Epsilon star. And again, the column space of x naught star is a subset of the column space of x star. And the distribution of properties of epsilon star is multivariate normal 0 sigma squared I. Now, so when we go from here to here, it's the same. So we're wondering, are some of these beta parameters zero, meaning we should be in this model, or not zero, which means we should be in this model. Now, the only loose end that I think is there is that if we assume this is true, so that this is in the column space of x, so x, does that imply that this is in the column space of x star? And so let's look at that, let's examine that. So remember, we want to be in this, we're in this model, this setting, but somehow we want to use this, transformed and simpler model situation, right? We've already developed partial f-tests for this settings. So if we can get away with it, let's do it. Then it's easy. And so let's prove this case. So let's assume that column space of x0 is in the column space of x. Then remember, if that's true, then there exists a matrix G such that x is equal to xg, right? So this is a matrix, and it can be represented as a column in the column space of x, and you do that like this. So we assume it's true, which is the saying, hey, we're going to assume this is true, and now we want to show that then this has to be true, and then we're going to use a simple model to develop the partial f-test. So we need to show that a vector in this column space is also in this column space, which means that this is a subset of that. So let's let, for some vector b, and I probably should have a little vector sign above that. So for some vector b, then x naught star can be represented, it is in the column space of x naught star, right? That's by definition, right? This linear combination. Now, then this vector right here, if we unpack x naught star, can be thought of as this, right? Or not thought of, it is this. But now, if this is true, then x naught can be represented like this. So for x naught, we plug in xg. Now this right here is x star, right? And then this is just a vector, so let's call it a. Well, this right here is in the column space of x star, so it is true. So if this is true, it implies that this is true. So which says that developing a f-test, a partial f-test in here, is equivalent to developing it there. And so that's what we're going to do. We're going to develop it in terms of this model, and then we'll unfold it back so it has the notation that's used for this model. So we need some background first. So the hat matrices, they're also projection matrices, and we've been looking at this. So the hat matrix for the full model is this. So X prime X inverse X prime. It's a perpendicular projection matrix onto the column space of X star. And the same for the reduced model, this H naught star. This is a perpendicular projection matrix onto the column space of X naught star. Now we do know that X naught star is a subset of X star. The column spaces are. Now by property 7 in a video I have called perpendicular projection matrices, that means this is a perpendicular projection matrix. It's actually onto the orthogonal complement of the column space of X naught star with respect to the column space of X. So what that means, if there's a vector dangling out in space and we pre-multiply it by this perpendicular projection matrix, it forces it into this column space but perpendicular to this. Right? It's a non-zero vector in this perpendicular to this. Now from previous videos 53 and previous videos 54, so I have a playlist called Generalized Linear Models Regression. In the 53rd video and the 54th video, we show that the rank of H is just the rank of H stars, the rank of X star, the rank of H naught stars, the rank of H naught star or X naught star, and then this, the rank of this projection matrix is this, the rank of X star minus the rank of X naught star. So now we need to look at some distributions of some quadratic forms. And I actually have a video called Distribution of Quadratic Forms if you want to look at some of the theorems that we're going to be using in this video. So if we divide y star by sigma, then it's easy to show that it's multivariate normal with this mean and covariance matrix I. So then, using this formulas in this video, it's easy to show that this quadratic form divided by sigma squared is a chi-square distribution with degrees of freedom, rank of X star minus rank of X naught star, and with non-centrality parameter lambda, which is 1 over sigma squared times the mean of this vector, with times this, times the mean of that. That's the distribution of it. So then, from previous video 53, where we look at the error variance, driving an estimate for it, we show that this is a central chi-squared with n minus the rank of X star, degrees of freedom. Now, in this video too, if we took the sum of squares residual, or sometimes called sum of squares error, divided it by this degrees of freedom, that's what we called the mean square error. And we showed actually that the mean square error is an unbiased estimate of the error variance sigma squared. So then the test statistic, we're going to defer to previous video 31 in this playlist where we derive it the formula and everything associated with it. When we want to test, is model 2B, meaning the reduced model, is correct, or is model 2A, the full model, is it correct? Now, equivalently, you can use it in 1B and 1A. Is this? So this quadratic form divided by its degrees of freedom. So this is a chi-squared divided by its degrees of freedom, and divided by an independent quadratic form divided by its degrees of freedom. So it's an F test. It's just, F is distributed with an F distribution with numerator degrees of freedom here, and the denominator degrees of freedom is associated with this, which is up here. And I'm pretty sure that this should have stars here. And non-centrality parameter lambda. So note under the null hypothesis that if this is equal to, the expected value of y is x naught star times beta, meaning the reduced model is true, then this is actually in the column space of x star, right? You can see that this is x star. We're taking a linear combination with these betas. That if this is true, so under the null this is true, but it's if and only if lambda is true. And one way to think about that, lambda is this, right? So this is a perpendicular projection matrix that if you pre-multiply it times some non-zero vector, then it shoves it in the column space of x star, but perpendicular to the column space of x naught star. So it's a non-zero vector in here. And so the only way for this to be zero is if this vector here is in the column space of x naught star, which says that it projects it into this but perpendicular to this. And the only way that can happen is if this is in the column space of that, and then it ends up being zero. So this is an if and only if it's zero, and then this in the column space of that, and if this is true, then lambda is zero. And I'm not for sure if I did that 100% justice, but you can kind of reason that out. So now let's rewrite. So this is the test, and we're done, and it's over, and we can end the video. But I want to rewrite this in terms of sort of model 1 being in the weighted least squares regression setting. So let's rewrite the numerator and denominator. But first, from previous video 51, where we look at the hat matrix in the weighted least squares regression setting, it is this. That's what it's defined. And it's an oblique projection matrix onto the column space of x. And then, so in the reduced model, we'd get something similar, where that's an oblique projection matrix on the column space of x naught. Notice there's no stars because we're in the model 1 setting. So here, now let's look at the hat matrices that we just used for our test statistic and rewrite them in terms of model 1. So here we unfold x star everywhere and we get this. Then if we post multiply by the identity matrix, so v to the minus 1/2, v to the 1/2, then what's in front, so this becomes v inverse, that becomes a, and we're left with this. And so similarly, you can do that for h naught star. It would reduce to this. So v is, of course, the v to the minus 1/2 is the inverse of the square root matrix. And v is the variance covariance matrix, the known component. So now let's look at this quadratic form. And since this is symmetric and idempotent, we can write it like this. So we don't need the tick because it's symmetric, but it's going to help us understand what's going on a little bit better. Now for H star and H naught star, let's plug in what we just derived. So we get this long expression. Now this transpose, when it goes in, it reverses these, of course puts a tick. These are symmetric, and then it reverses that. So then when we left factor out a v to the 1/2, we get that, and we right factor out a v to the -1/2, and we get this. And so the same here, we left factor out a v to the -1/2, and we right factor out a v to the 1/2, and we get this. So this is the identity matrix, that's v inverse, and that's the identity matrix, so we're left with this. And then we're finished. So everything is in terms of the weighted least squares regression. Now from previous video 53, we derived the expression for the mean square error, which is the sum of the squares residual, or sum of squares error, divided by its rank, n minus the rank of x. And we derived that it's this. So now the test statistic, rewritten in terms of model 1, is this right here. And this is what you see in the literature. Now the only remaining loose string is the non-centrality parameter. So let's look at that. So if using a similar approach to what we did up here, you can show that it's equal to this, right? So this is the non-centrality parameter. But we need to show that if it's 0 for model 2, you know, that when we're testing the model 2 setting, that it's also 0 in the model 1 setting. So let's look at that. So if the lambda is 0, then the expected values in this column space of the reduced x naught star. But if we unfold that, we just get this. So it's if and only if, because it's the same thing. But now if this is in the column space of x, we can write it as a linear combination of this, right? And so v to the -1/2, expected value of y is x beta. And then we have, it can be written as a linear combination of this. So we get b times its vector, and this is for some vector. Then we can post multiply by v to the 1/2, and we get this. But this is saying this is a linear combination of the column space of x, right? But that's the mean of y, and it's in the column space of x. And so it's true that it's, if this in the reduced model, the column space is reduced model, it's 0, and vice versa. Well, that's all I have for this video. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.